And today's speaker is Ben Knudsen from Northeastern, who will tell us about topological complexity of pure graph braid groups. Take it away, Ben.
Hey, thanks, Dan. Thanks for the invitation. Thanks all of you for coming. I'm going to try to share my screen here. Hopefully you can see my screen.
It's good.
Awesome. Okay, so yeah, I'm going to tell you about something about the topological complexity of pure graph braid groups today. So I'll start with the definition that's behind everything, which is no doubt familiar to many of you. So this is all about configuration spaces. So the configuration space of K ordered points in some fixed background space X is this. So it's the space of all K tuples of points in your space that are all different. So I take the Cartesian power and I remove all the diagonals. And an idea that is probably familiar to everybody in this seminar is that something about the problem of motion planning in X is captured by this number, the topological complexity of X. I'm not going to define the topological complexity. Probably all you know the definition. I will remind you unnecessarily of the few things that I need to know about it for this talk. So it's a number, and it says something about instability of motion planning, or the number of domains of continuity of a motion planning algorithm in X. And if you want to insist that you have collision-free motion planning of multiple bodies in your space, that's captured by the topological complexity of a different space, namely the configuration space of the number of bodies in your background space. And I'm going to focus on the ordered case today. So the unordered case is also super interesting, but that's not what I'm talking about today. Okay. So there's a picture of a point in the configuration space of 3 points in the torus. And as a convention, I should say that I regard the topological complexity of a point to be 0. Some of you may regard the topological complexity of a point to be 1. And I believe that both of these conventions are quite common in the literature. I'm using this sort of reduced convention. Okay, so topological complexity of configuration spaces, collision-free motion planning, lots of work has been done on this topic. So it's a theorem due to Farber and Uzvinsky in some cases, and Farber and Grant in general, that calculates the topological complexity of the configuration spaces of Euclidean space. And this is the answer. And the theorem of Cohen and Farber calculates the topological complexity of a closed orientable surface of genus G. And this is the answer. And something that I would like to point out about these answers is something slightly vague, which is independence or eventual independence or sort of independence of relevant parameters in question. So the answer for Rn is basically independent of n up to the parity. And the answer for a surface is independent of the genus as soon as your genus is not too small. Okay. So there's an idea, and that idea is today called topological robotics, or that's a simplification, but kind of true. In many real-world situations, you want to consider your background space to be a graph. So you imagine that you're talking about an automated factory, or like a road system with self-driving cars, and you want to allow your automated guided vehicles to move around in this space without colliding with each other. And so that puts you up against the topology of the configuration spaces of the graph. And I guess I should say, in order to explain the title, although I doubt many need an explanation, the configuration spaces of graphs are all aspherical. So they are k-pi1 spaces. And so everything about them is determined by their fundamental groups. Those are called the graph braid groups. So that explains the appearance of that phrase in the title. All right, so there's a graph, and there are some points hanging out on that graph. All right, so as a piece of notation, I'm going to write m of gamma. This is Farber's notation, I believe, for the number of essential vertices of my graph. So an essential vertex for me is just a vertex of valence greater than or equal to 3. They are essential because they are topological features of the graph, and in fact, even isotopy invariant features of the graph. So a bivalent vertex is sort of extra combinatorial data that is not remembered by the space. And a univalent vertex is sort of not there up to isotopy in the same way that the boundary of a manifold is not there up to isotopy. So the essential vertices are sort of the isotopy invariant information about the graph. Okay, so the theorem I have to tell you about today is the following. So we're going to look at a connected graph, and we're going to assume that the number of essential vertices is at least 2. There aren't a lot of graphs with 1 or 0 essential vertices. You can probably think of all of them very quickly. And those are easily treatable, or at least treatable by other methods. So if there are no essential vertices, then we're talking about a manifold with boundary, perhaps. And there's not a lot of interest, not a lot of interesting things that happen in the configuration spaces of one manifold. And the case of a single essential vertex is more interesting, but is treated elsewhere. So we're going to assume this. And so the theorem says that as long as the number of points that you have is at least twice the number of essential vertices, then the topological complexity of your configuration space is exactly equal to twice the number of essential vertices. And I will point out a feature of this answer, which is both similar and not similar to the previous answers. It displays some kind of independence of the relevant parameters. In this case, it's independent of k. So that's a commonality that it has, but a difference that it has is that it's independent of k. So the other answers were all dependent on k, and this answer is not dependent on k. Okay. And that independence will be explained momentarily. Are there any questions so far about statement of the theorem or my conventions? Okay, so this was conjecture by Farber, and partial results were known, but not in general. So trees were known, and I guess trees with loops and sort of mild generalizations of trees with loops were known, but not the general case. And the answer when the number of points is small relative to the number of essential vertices, I believe, is not well studied at this point. So that would be an interesting thing to understand. Okay, so to sort of get in the direction of how the proof works, let me show you an example of something that happens in configuration spaces of graphs. This is the first interesting thing that happens. It's when you have 2 points and they're living in the star graph with 3 leaves. I guess stars don't really have leaves, so my metaphors are getting mixed. But in any case, S3 is the cone on the discrete set 1, 2, 3 with the canonical CW structure. I guess I should have said a graph for me is just a finite, at most one-dimensional CW complex. Okay. So here's a game that you can play in this graph. You can have 2 points, and you can move one of them through the central vertex onto the unoccupied leg. Stars also don't have legs, but in any case, and then you can move the second particle onto the now unoccupied leg that the first particle vacated, again, using the central vertex. And that leads you to the second picture, and then you can keep doing this. You can move the first particle onto the only unoccupied leg and then do the same thing with the second particle. And then you can do that a third time. And if you do that a third time, you end up back at the place you started in. And so this concatenation of paths is a loop. And the class of that loop is non-zero in pi 1. This is the first interesting thing that happens. And in fact, the map that you get as a result from the circle into the configuration space of 2 points on this graph is a homotopy equivalence. So that's the only game in town for this number of particles in this graph. Particles can orbit each other by taking turns passing through the central vertex. Okay, so this leads us to an idea. Anytime you have an essential vertex, you in particular have 3 legs. You have an embedding, non-canonical, non-unique, but you have an embedding of this star graph with 3 leaves into your graph at that essential vertex. And thereby you get an embedded circle inside of your configuration space of 2 points in your graph. It's just by allowing the 2 particles to do this move locally at that vertex. And thereby you get an embedded circle in any configuration space of a larger number of points just by letting the rest of the points sit stationary somewhere far away from where the action is happening. Okay. And well, if you have more than one essential vertex, then you get an embedded torus. You can let 2 particles hang out near one of the vertices and 2 other particles hang out near another of the vertices and so forth. Again, this depends on choices. You have to choose which of the half edges at each essential vertex you are using, and you have to sort of choose an orientation, and you have to also say which particles are 1, which is 5, which is 7, because we're in the ordered configuration space. But in any case, anytime you have R essential vertices, there is an embedded torus that looks like this in the configuration space of 2 R points. And for the same reason, you thereby get an R-dimensional torus in the configuration space of any larger number of points by letting the rest of the points hang out, doing nothing far away. Okay, any questions about this idea? Okay, so if you take this idea seriously, then you should believe that the dimension of the configuration space of k points is greater than or equal to the number of essential vertices as long as you have enough particles to do this move. You have this embedded R-dimensional torus inside of your configuration space, and as it turns out, the fundamental class, the push forward of the fundamental class of this torus is non-trivial in homology. And so that tells you that the dimension is at least that large. Okay. Well, there's a theorem of Fiokovsky that says that, in fact, the configuration space deformation retracts onto a cubical complex whose dimension is at most that large. And I won't say too much about the Fiokovsky complex. It's all that in a bag of chips. It's a really good thing to have, and you can do a lot with it. But I'm not going to say too much about it right now. So what this says is that as long as you're in the large enough number of points range, the homological lower bound from this torus and the geometric upper bound from this cubical complex agree. And so that is actually the dimension. Okay. And that's independent of k for large enough k. So what the theorem is saying is that actually TC is twice the dimension as long as you are in the range where that is in fact the dimension. Questions about any of this so far? Okay, so this suggests a very vague strategy to try to prove the theorem. As I will remind you in a moment, you have an upper bound on TC that's given by the dimension and a lower bound on TC that's given by something in terms of cohomology. I will be more precise momentarily. We have here a upper bound in terms of the dimension and a lower bound in terms of homology that happen to agree. And so the strategy is to try to replace homology with cohomology and then win. And the problem with that strategy is that we don't know anything about the cohomology of configuration spaces of graphs. Okay, so that's a little sad. So I'll remind you now of the thing I just alluded to. So the Theorem of Farber says that TC is sandwiched between two things. One is twice the dimension of your space, assuming your space is reasonably nice. And the other is the zero divisor cup length of your space. I'll remind you what that is. So DCL is the largest number so that you have that number of cohomology classes in the product of the space with itself. That cup to something non-zero, and whose pullback along the diagonal is zero. So having the delta star of zeta I equal to zero, that's called being a zero divisor. And so R is the largest length of a non-trivial product of zero divisors, hence the name. Presumably this is familiar to many people in the audience. Are there any questions about any of this? Okay, so as I said, we don't know anything about the cohomology of configuration spaces of graphs. That's a hyperbolic statement. We know some things about it, but not really a lot at all. We know quite a lot about the homology and very little about the cohomology. So instead of trying to prove the theorem, which I can't do, I'm instead going to think about an example that I do know something about, which is configuration spaces of Rn, or R2 in this case. So we know a lot about the cohomology of the configuration spaces of R2. We know basically everything. So this toy example, which seems like it has nothing to do with anything that we're talking about, but secretly does, is the following. We're gonna give a bad lower bound on the TC of configuration spaces of an even number of points in R2. So the theorem from before says that this is not at all the TC. The TC is much larger. But here in this example, we're gonna show this. So how are we gonna do it? We're gonna do it using Farber's theorem. So we're gonna cook up some cohomology classes and multiply them together and get something non-zero. That's the hope. Where do these cohomology classes come from? They come from the Gauss map gamma that goes from the configuration space of 2 points to the circle, and gamma just measures the unit vector from point 1 to point 2. So there's a depiction of the unit vector from point 1 to point 2, and we get a section of gamma, iota, by including the circle into the configuration space as a pair of antipodal points. Okay, and it turns out that these are both homotopy equivalences. That's actually the inclusion of a deformation retract. And so all of the information in the configuration space of 2 points in R2 is sort of the circle that is shown here in red where 2 points are orbiting each other. And so we get cohomology classes in the configuration space of a larger number of points. It's not important that k is equal to 2d here, but that's the example that we're in. So let's be concrete. I can use the coordinate projection onto the ith point and the jth point to get to the configuration space of 2 points, and then I can go into the circle using this Gauss map, and I can pull back the preferred generator of H1. I should have put a 1 there instead of a star, but that's okay. And that cohomology class is called alpha ij. Any questions at this point? This is quite classical. Okay, well, we can do something slightly more systematic than that. So if we want to have more complicated cohomology classes, we can just take a collection of subsets of 1 up to 2D, each of which has cardinality 2. And we could just multiply together alpha ij for each ij that happens to be a member of lambda, this collection of subsets. And that's going to be a class called alpha lambda, and that's going to live in the lambda size of lambda cohomology of the configuration space of 2D points. Okay, great. And this is independent of the various choices. I mean, I guess secretly I'm working mod 2, and so the only ambiguity here would be a sign, and so we don't care about that. But okay, let's not worry too much about the signs. And I can get a zero divisor in a similar fashion. So what can I do? I can take each for each ij, which is a subset of 2 points that lives in lambda. I can take alpha ij, and I can build a class in the cohomology of the square of the configuration space, which I'm using the Kuna theorem to regard as the tensor square of the cohomology, by just saying it's alpha ij tensor 1 plus 1 tensor alpha ij. And we're working mod 2. And so that's a zero divisor because pulling back along the diagonal is given by multiplying the thing on the left side of the tensor with the thing on the right side of the tensor. And so if I do that to this alpha ij tensor 1 plus 1 tensor alpha ij, I get 2 alpha ij, which is 0. So each of those individual things is a zero divisor. And so their product over lambda, this collection of subsets of cardinality 2, is also, well, it's a product of zero divisors. Okay. Any questions about this? I may have said a bunch of notation quickly. I don't know. Okay, so the lemma is that if you choose your lambdas judiciously, so remember, each lambda 1 and lambda 2 are both collections of subsets of the numbers 1 up to 2D, and those subsets have cardinality 2. So it's just a collection of pairs of labels for particles. And if I choose them so that for each collection, the pairs that I choose are pairwise disjoint, so 1 does not appear in more than one of them, for example. And if the collections themselves are also disjoint, so I don't have the same subset of 2 points in lambda 1 as in lambda 2, so 2 different disjointness conditions, then the product zeta lambda 1, zeta lambda 2 is non-zero. Okay, and so, well, if we believe that, then since this alpha ij tensor 1 plus 1 tensor alpha ij is a zero divisor, then I now have the lower bound that I wanted, 2D, on, because zeta lambda 1 times zeta lambda 2 is a product of 2D zero divisors. As soon as I can find lambda 1 and lambda 2 of cardinality D each that satisfy these two properties, and here's an example, I can take lambda 1 to be each consecutive pair of numbers, and then I can hit that with a cyclic permutation to get each consecutive pair of integers except shifted by 1 and wrapped around. And lambda 1 and lambda 2 here do satisfy these two conditions. Okay. So I should say that this strategy to prove this kind of bound is not due to me. I guess it's probably due to Farber, and has been used many times in various contexts, and is, I believe, the background strategy behind all of the previous partial results toward the theorem that I'm trying to tell you about. It's this strategy applied to some cohomology classes in the configuration spaces of the graph. Build zero divisors in this way and multiply them together and try to see that they're non-zero. Okay. Okay, great. So why is the lemma true? I'm not going to spend too much time on it, but it turns out that the product is detected by a torus. And how does the torus work? Well, in the configuration space of 2 points, I have this circle that I wrote down earlier, which is given by this map iota, the inclusion of a pair of antipodal points orbiting each other. And so for each pair of points, ij in lambda1 and each pair of points ij in lambda2, I have an inclusion of a circle into the configuration space of 2 points. So that's this first map. And then the second map is just obtained by choosing a bunch of disjoint embeddings of R2 in R2 and putting the pictures inside each one. So here's a schematic of what it is. The whiteboard is R2, and each of these dashed circles is an R2 inside of R2. And I just plug in what was happening in the configuration space of 2 points in R2 into these smaller R2s, and I get something in the larger configuration space. Okay. And it turns out that this torus inside of the square of the configuration space detects this product, and that's why it's non-zero. So are there any questions about any of this?
Looks kind of operatic.
It's totally operatic. Yes, absolutely. This is, we are using structure maps for an E2 operatic. And in doing so, I betray my background. Any other questions?
I have a question.
Yes.
So in the lemma, in the statement of the lemma, you require that the members of lambda1 and lambda2 are pairwise disjoint, but then it doesn't seem to be the case in the example.
Sorry, so I guess there's some ambiguity in the statement of the lemma. So what I'm saying is that for each I, the members of lambda I are pairwise disjoint. And that is true in the example. So it's true that the members of lambda1 union lambda2 are not pairwise disjoint. Like 1, 2, and 2, 3 share the element 2. But lambda1, the elements of lambda1 are pairwise disjoint, and similarly for lambda2. Thank you for clarifying.
Okay,
that.
Sure. Thanks.
I don't know if there, oh, there might be questions in chat. I have not been looking at the chat at all. So if you had questions and put them in the chat, I would be happy to hear them spoken out loud if you want to do that. Okay. So moving on. So actually, this toy example, which only goes to give a bad bound for the TC of the configuration spaces of the plane, actually already proves the theorem in the planar case, the case of a planar graph, which already was not known. So the observation is that two different homology classes are the same. So there's the circle on the left, which is a pair of antipodal points rotating each other in R2 via this embedding iota. And there's the picture on the right, which is a pair of points orbiting each other by taking turns passing through the central vertex of an embedded star graph inside of R2. And if I regard those as homology classes in the configuration space of R2, they're the same homology class. Okay, so let's prove the planar case. We're going to choose an embedding of our graph in R2. So it's planar, we can do that. And we're going to take D in the previous example to be at most M of gamma. Okay. Now, the observation is that the restriction of this cohomology class, zeta lambda 1, zeta lambda 2, to the configuration space of the graph. So I have an embedding of the graph in R2, and that means I have a map from the configuration space of the graph to the configuration space of R2. Configuration spaces are functorial for injective continuous maps. And so I can pull back this cohomology class to the configuration space of gamma. And it is non-zero because it's detected by this torus. I have D less than or equal to the number of essential vertices of the graph. And so that means that I have enough particles to have an ith particle and a jth particle rotating each other through an essential vertex for every ij in lambda 1 or lambda 2. Okay. And so the reason this detects it is that, well, the previous picture, I can go back. The previous picture, I should have maybe emphasized this, doesn't depend on the placement of these R2s inside of R2. So the space of embeddings of D R2s into R2 is connected. And so that torus doesn't matter. It doesn't care whether I move these R2s around inside of R2. So I can put them wherever I want. And so in particular, I can put them centered around the essential vertices of this graph which is embedded in R2. And then I can let pairs of particles orbit each other by passing through the essential vertex. And then by this observation, the fact that two antipodal particles orbiting is homologous to two particles orbiting by passing through an essential vertex, we see that the previous torus has the same fundamental class as this torus. And therefore, that torus detects the restriction of zeta lambda 1, zeta lambda 2 to the configuration space of the graph. Well, and then that was for the configuration space of 2D points in the graph. If I have more than 2D points, then I can just use coordinate projections to get rid of all but 2D of them. And it's not hard to show that the further restriction of zeta lambda 1, zeta lambda 2 along this coordinate projection is also non-zero. And so that tells you that for any D that is less than or equal to the number of essential vertices of the graph, the zero divisor cup length is greater than or equal to 2D. Okay. And that's what we wanted to show, because I can set D equal to M of gamma, and then the lower and upper bound agree. Questions about any of this so far? I guess I could take a look at the chat and see what it says. Ah, okay, great. It sorted itself out. Okay. Any questions before I move on? I should say that I have no idea how long this talk is, in the sense that I have no idea how long the slides that I wrote are. I know how long my talk is supposed to be. Okay. So in general, of course, graphs are not planar, so sad, this doesn't work. But the spanning tree of my graph is planar, and I can embed it into R2, and that embedding extends to an embedding of my graph into some orientable surface. So even more specifically, my graph is the one skeleton of a CW structure on this orientable surface. Okay, so so here is the picture. We had our graph, and we can put it inside of a surface. The surface is blue, or I guess the boundary of the surface is blue. And the spanning tree of my graph, or a spanning tree of my graph, is embedded inside of a copy of R2 that's embedded inside of my surface. So the copy of R2 is depicted in green. And I have this diagram, spanning tree, which is T inside of my graph, inside of my surface, and the tree sits inside of R2, inside of my surface. And the planar case applies to T. So I have a lower bound on TC for my spanning tree that comes from Coronology classes in the configuration spaces of R2, this green R2, this specific R2. And so I would win if I knew that those Coronology classes came from the configuration spaces of the surface, because those Coronology classes are detected in the configuration space of the tree by this torus. And that's like a deeper detection than I actually need. I need them to be detected at the level of the configuration spaces of gamma. And so if they are non-zero after restricting to the configuration spaces of T, they are certainly non-zero in the configuration space of gamma. So as long as I knew that these special Coronology classes that I'm working with came from the configuration spaces of sigma, then we'd be all good. And so really it's enough to show that alpha ij, so if we remember how the Coronology classes were built, the Coronology classes were built out of these alpha ij classes by saying like, okay, take one tensor alpha ij plus alpha ij tensor one, and then take a product of these things. So like the basic building blocks are these alpha ij's. And so it would be good enough to know that alpha ij lies in the image of the restriction on Coronology from the configuration space of k points in sigma to the configuration space of k points in R2. Any questions about this reduction? Okay. So that's where this proposition comes in. So let's say you have a connected, oriented, open surface. It is crucial that the surface not be closed. The statement is false for a closed surface. So there's a class which I'll call alpha ij sigma in the first Coronology of the configuration space of k points in sigma, whose restriction to the configuration space of R2 along any embedding of R2 is equal to alpha ij. Doesn't matter what embedding you take. Okay. So so how does this go? So I can choose metrics. I can choose a metric on my surface, and really the statement about every embedding of R2 is not all that special. Like the space of orientation preserving embeddings of R2 is connected, so it really suffices to consider a single one of them. And if I have an orientation reversing embedding, then I can just compose with an orientation reversing embedding of R2 into itself. And we are in dimension 2, and so alpha ij is equal to alpha ji. And so, okay, so really it's enough to just focus on a particular embedding of R2 into sigma and show that there's some class alpha ij that restricts to alpha ij sigma that restricts to alpha ij along that particular embedding. And so I can choose a metric on my surface and put the restricted metric from that metric on R2, and I can consider the exponential map for that metric. So I have the circle bundle of the tangent bundle of sigma, and I get a map from that into the configuration space of 2 points in sigma by just keeping my first particle in my configuration at the point where the tangent vector was, and putting the second particle in my configuration at the time 1 exponential flow away from that point. Okay. So there's a map like this, and there's a map like this, and this diagram commutes. So on the right, there's the embedding, there's the map from the configuration space of 2 points in R2 into the configuration space of 2 points in sigma. That's just induced by the embedding of R2 into sigma. And similarly, I have the map on the circle bundles of the tangent bundles, and this exists because I am using the induced metric on R2 from the metric on sigma. And in fact, the top map is a homotopy equivalence. This is basically the same fact as before, that the configuration space of 2 points in R2 is homotopy equivalent to a circle. I'm just saying it in a slightly different way. And so it would be good enough to know that the starred maps induce surjections on Coronology, right? I'd like to know that alpha ij is in the image of the induced map on Coronology of the right-hand vertical map. And if I knew that all the other 3 induced surjections, then I'd be done. Any questions about any of this? Okay, so let's think about the first starred map. That's the map from the sphere bundle of the tangent bundle of R2 to the sphere bundle of the tangent bundle of sigma. Well, that surjects on Coronology because both of those bundles are trivial. And we're using, for the first time, that sigma is an open surface. There are no non-trivial S1 bundles. Okay. Great. What was the map star star? The map star star was this exponential map from the sphere bundle of the tangent bundle of sigma to the configuration space of 2 points in sigma. So why does that surject on cohomology? Well, it turns out that both of those things are actually fiber bundles over sigma. So I can project the configuration space of 2 points onto sigma by just forgetting one of the points. That's the Fidelnoy-Wirth fibration, and the fiber of that is sigma minus the point that I forgot. Or sorry, sigma minus the point that I remembered, excuse me. And of course, the sphere bundle, the tangent bundle of sigma is a fiber bundle over sigma with fiber the circle. So I have this map of fiber bundles, and the Sayre spectral sequence for both of them collapses. That's easy to see for degree reasons, and we're again using the fact that sigma is open, so it doesn't have any degree 2 cohomology. And this this top map from the circle to sigma minus a point, if you think about the definitions like the exponential map, blah blah blah, this is actually an embedding of a geodesic circle around the puncture. That's what that map is. And that map, the embedding of a circle around the puncture, induces a surjection on cohomology. And so since the Sayre spectral sequence is collapsed, and since the map on base and fiber surjects on cohomology, so does the map on total spaces. Okay. And that is, that's all I have to say. So that concludes the proof of the proposition, which is that there is some lift of alpha ij to the configuration spaces of the surface. And that was the last ingredient that we need for the theorem. So I am done. 42 minutes. Okay, that's seems good.
Thank you very much, Ben. Let's open it up for questions now. Anybody feel free to jump in.
Ben, I have a question. I think I already mentioned this, but it would look like many of these techniques would generalize to higher TC more or less directly. Would that be true?
Yeah, so I think that's absolutely right. So instead of zeta lambda 1, zeta lambda 2, you'd have a lambda 1, a lambda 2, and a lambda 3. And you'd run the same argument, and it would tell you that higher TC in the appropriate range is equal to the appropriate multiple of m of gamma. Yeah, I think it generalizes without any, essentially with no change.
May I ask, in the unstable range, so when you have few points moving around, what are the best lower and upper bounds that you can get with this method?
Yeah, so so there, I will say that they're not sharp. So there's an upper bound on the dimension that so Fiokovsky's theorem has a more precise, sharper statement where the dimension is takes into account the Euler characteristic of the graph in addition to the number of essential vertices. But that upper bound is not always realized by TC. There are examples that show that. And the lower bound that comes from this kind of star graph torus focused point of view is also not sharp. So I mean, you can run this anytime you have an essential vertex, you can put 2 points there and you can run this strategy, but it will not be sharp. So I think the example, I'm not going to be able to quote the right numbers off the top of my head, but the example to think about is the configuration space of 3 points in a suspension of 4 points. So a theta graph with 4 edges. So I just have 2 essential vertices and 4 edges going between them. Looks like a little bunch of bananas. And the configuration space of 3 points in that graph turns out to be homotopy equivalent to a surface of genus like 13 or something. In any case, not 1. So there are interesting, mysterious, exotic classes in homology that are not tori, I guess is the upshot in configuration spaces of graphs. And we have no systematic understanding at all of what they are. So that's like the first example of such a thing. But there are more. You can turn the recipe that gives you that class into a general recipe for generating higher classes. So there's an infinite family of, I don't know if anyone's checked that they're non-zero, but they must be non-zero. Classes that do not come from taking sort of disjoint unions of pairs of points orbiting circles, non-toric strange classes, and we just don't have any. It's a jungle out there. So I think that any understanding of well, I don't know about that. That's probably too strong of a statement. In order to try to push this kind of approach farther, I think one would need to grapple with those homology classes and to what extent they are, to what extent they can be detected by cohomology classes. There's so maybe what I mean to say is that this approach might not be the right approach for understanding the unstable range because because of the presence of these strange homology classes. Like this is really this approach is an approach that says, I don't understand cohomology, I understand homology, and so let's just try to get as far as possible using homology. And I guess what I'm saying is that in the unstable range, the knowledge of homology is not there. So yeah.
I have a question, if I may. Can you hear me?
Yes.
Okay. First of all, thank you for your talk, and it's a beautiful result, and the proof is very elegant, the instruction is very clear. Thank you, and also thank you for organizing a workshop. It was a year ago, but it looks like it was 10 years ago. It was pre-COVID time. It was a very nice workshop.
Right before COVID.
Yes. So I have 2 questions. So one question is the following. So if I fix a graph, I mean gamma, and I look at this configuration space of n points on this graph, but when n is large, the graph is fixed, but n is large. So, well, we know that TC doesn't change, it stabilizes, right, from your theorem, for example. But can we, do we know, I mean, what happens to the spaces themselves? I mean, they definitely are not the same, right? The dimension is different, right? So, I mean, there's, so it must be something simple happening, some kind of construction, some stabilization, but not stabilization in the sense that they become equal. They are not equal, but some kind of suspensions. I don't know. I think it's an interesting question. And I have another question, which is also, I think, is interesting. So let's look at configuration space of endpoints in RD, and also endpoints in RD plus 2. We know that these two spaces are, well, very different spaces, but TC is the same. Is it possible to I don't know, to have a direct proof that TC is the same? Because the proof of that fact that TC is the same goes through different computations and not direct proof. There is no direct connection. This would be interesting to see. So I mean, it's very general question, so I'm not exactly about your talk.
Well, I think those are great questions. So to the first question, I think that is an absolutely fascinating question that I've thought a lot about from the point of view of homology. So so my collaborators and I have calculated we have an asymptotic formula for the Betti numbers of the configuration space, unordered configuration spaces. So in the ordered case, that's something that I would like to do, but have not done. But let's just talk about the unordered case because that's also interesting. So there's an asymptotic formula for the Betti numbers of these spaces, and what the formula tells you is that asymptotically, although there are lots of exotic classes that are not tori, asymptotically there aren't. So somehow the growth of these exotic classes is strictly slower than the growth of the toric classes, and so they're drowned out in the limit. And so in the limit, all homology is actually captured by these pairs of particles orbiting each other near essential vertices. That's the only thing that happens asymptotically, and so that has some interesting consequences. Like, for example, one of the open questions about configuration spaces of graphs is torsion. There's almost nothing known about torsion in the homology. There's the fact that H1, that the two torsion in H1 detects planarity of the graph, but there's no known example of odd torsion in the homology. And so this asymptotic formula tells you that asymptotically the homology is torsion free. Although there could be homology sort of somewhere, it grows too slowly to contribute to the asymptotic calculation of the homology. And so I think it would be super interesting to have some kind of space level understanding of that asymptotic statement. Somehow in the limit, these configuration spaces are built somehow from circles, from spheres, from tori in some kind of controllable way. But I don't know. I don't even know how to really articulate what that space level result would be. And to your second question, so there's a trick. I'm reminded of a trick that I probably will not be able to get exactly right off the top of my head. It's a trick that I learned from Dev Sinha, and maybe Dev learned from Nick Proudfoot. I don't know if Nick Proudfoot invented the trick or learned it from someone. But it's a way to directly relate configuration spaces whose in Euclidean space whose dimensions differ by 2. It's something like the following: you regard the last 2 coordinates as a copy of the complex numbers, and you let the circle act on the complex numbers as the unit complex numbers, and it thereby acts on the configuration space. And this is the part where I'm not going to remember. It's either the invariance or the co-invariance or the homotopy invariance or the homotopy co-invariance of that action, it turns out, is the configuration space of RD rather than RD plus 2. So somehow whichever group cohomology type operation I'm talking about is appropriate, has the effect of lowering the dimension of the ambient space by 2. So I suspect that there would be a way to directly prove the thing that you're talking about by sort of assuming that it's true for R2 and then, you know, bootstrapping our way through these relations. But I would have to sort of go back and remember exactly what the precise form of the trick is.
Thank you. Thank you.
That's very interesting. Any further questions? Feel free if something comes up. I am going to pause the recording now and let's